Hi, so before we get into the real nitty-gritties about quantum theory, we are going to talk about waves, particles, how they fit together, because that is a huge part of quantum theory. So this video is going to be that little bit of an introduction. We're going to talk about waves, we're going to calculate energy, because all of that is super important on how we got to where we are today. It started with Bohr and his quantum leaps and the energy that he saw, and then it transformed into these things called orbitals and all that kind of stuff. So today there's going to be, we're going to look at energy and what color things are, how can we actually calculate how much energy those electrons can move. And it will start piecing things together. So at the beginning, you're probably going to be like, what in the world are we talking about? Why this doesn't make any sense, but then you'll see how all of it gets put together at the end. So make sure you take out your notes. I know you took some last night, so add a little bit to them. And then we're going to do some practice problems and things like that. So with that, so 5.1, waves, light, how are they all related? So you might want to pause this so that you can write down this as a topic. EQ, today's date is the 23rd, so make sure you get those written in. Those are what that is what I will be talking about or looking for when I'm checking your notes. Okay, so just as a reminder and a refresher, we looked at Niels Bohr. That's kind of where we ended in our last unit. And he worked under Thomson and Rutherford both. And he realized that electrons must follow orbits. They must be in these set paths like our sun. All right. And this is more than likely what you've been taught in middle school. You maybe went into a little bit more detail in ninth grade in physical science, but this is really the basic model. And it works, but it doesn't work. And you'll see kind of why. Okay. So with the planetary model in middle school, we always filled electrons in shells. I think of like a jawbreaker, which has multiple layers to it, or onion. Okay. So the ones that are closer to the nucleus, they fill the lowest first, and then further and further away, you get into higher energies, they fill it more. Okay. So also with this model, electrons can only be in the set paths. Okay. And so this worked for what was happening at the time, but it didn't quite work for all. All right. And so with Bohr's model, hopefully this will work. If it doesn't, okay. Nope. I need to have flash. So, yeah, Bohr's model, it worked for if we just had 2, 8, 18, 32, they were in these sets amount. And you're going to see where these come into play, the 2, 8, 18, and 32 in a little bit. Okay, so in these set energy levels, or in these set amount of energy, this is called a quanta or quantum, which in plural is quanta. So this is a really key vocab word. And it's the electrons can exist with this certain amount of energy. Okay, we will be able to calculate that energy as well. So Bohr's model, what happened is it worked for hydrogen, it didn't work for some other models. All right, in the video, he was talking about their quantum leap, like a hotel that we watched. But other people, some worked under Bohr. All of these kind of came up with this quantum model of the atom, and it's really kind of a couple people's ideas put together. Okay, and so the first thing that happened is that with quantum theory, the thing to realize is that electrons happen in both particles, and they also act as waves. So wave is just like light waves, things like that. But electrons can act as both particles and waves. So we're going to talk about this. The first thing with waves is first, and let me back it up. How they figured out that they act like both is they were doing this double slit experiment. So they would see these different wave patterns come about. So they realized that, okay, electrons, it was shooting out electrons were shooting out in these different guns, and if we had different slits, what would happen? And so that is really how they determined that this must be happening in both. Okay, so waves themselves are just a disturbance that transmits energy. So if you think about when you look at an ocean, there's not being any more water that's being added, but there was a disturbance that happened. Okay, if you think about a tsunami, there was an earthquake that happened underneath, and that's why all of a sudden there's energy that's being transmitted, and it makes that big ginormous wave. It pulls the water out, and it's just all this energy that's being transferred. Okay, if you have water's the one that I use water waves a lot because it's ones that we can see. Most of the other ones sound, light, heat, we can't always see them. With heat, you can a little bit, like if you have a grill open, you can see the little wave particles that are happening. Okay. Light waves are also known as electromagnetic radiation. That's going to be key, especially when we talk about colors. So electrons can also move as waves. All right. So some properties, you saw this yesterday in the bell ringer, but wavelength, um, it is from peak to peak or trough to trough. So if you look at this first diagram, okay, the red arrow here with wavelength, it goes from the same spot on each wave. So from wavelength, so crest to crest or trough to trough, those are considered one wavelength. All right. The unit that we use is meters or nanometers. Okay, amplitude, we are not as concerned with amplitude, but it's just height from the origin, so that middle line to the crest, so to the top. Okay, and then frequency, if I stood at one spot, how many times would the waves go past that point per unit of time, so per second? So it's hertz is the actual unit, but if you break it down, if you derive it, it's per second. So 1/seconds is the unit of hertz. Okay, so if you look at these two bottom waves, if I were to stand where it says time, the top one is going to move past me a lot faster. So that has a higher frequency, whereas the lower one, okay, it wouldn't move past me as far as much, but it has a longer wavelength. So the longer the wavelength, the lower the frequency. Okay, and so that was definitely a question on your poll activity that you saw. Okay, so with the electromagnetic spectrum, what happens is if they have longer wavelengths, so radio waves have a super long wavelength. TV AM is the one that usually has the longest, so it's almost 100 meters for to have one wavelength for an AM radio, which is why AM radio tends to be a little bit, fuzzier sounding because they have those super long wavelengths. All right. Gamma rays are the ones that have the smallest, have the shortest wavelength. Therefore, they're going to have a really high frequency. Okay. In the visible light, this is again is the activity that you guys did yesterday. And purple has the shortest wavelength. It's going to have the highest energy. Red is going to have the lower energy and longest wavelengths. Okay, and the way that I think about this is ultraviolet UV rays are things that can cause us cancer. It is well known, and so therefore they must have a lot more energy than like infrared goggles that don't do us any harm. Okay, so this is definitely something you have to know. Purple has shorter wavelengths and they have high energy. Red is less. All right, and that is something that Bohr used and other scientists used to kind of create these quantum leaps, being in a hotel, things like that, that were from our video. Okay, so we actually want to calculate these wavelengths. So wavelength is inversely proportional to frequency. So if wavelength goes up, frequency goes down, and then vice versa. So when you multiply them together, you get the speed of light. Okay, so the speed of light is always the same. We're going to use 3.00 times 10 to the 8th meters per second. So if we're actually calculating that wavelength, calculating that frequency at 588 nanometers for yellow light, what would that frequency be? Okay, so setting up the problem, you should write down what's in yellow. All right, and then you should always write down what equation you're going to use, because we're going to have two, maybe three that are really similar, and sometimes we'll use them both in a single problem. Okay, so we are looking for frequency, which is this F. Okay, so I'm going to rearrange it so that I get F by itself. And this is what I want to see. All right, then plug in your numbers. We know that we have the C is the speed of light, so it's 3 times 10 to the 8th meters per second. And then we know our wavelength, it gives us that in our problem. So it's 588 nanometers. Okay, now before you move on, notice how meters and nanometers, those are two different units. So you want to convert nanometers into meters. And the easiest way to do that is, you know that nano means 10 to the negative ninth. So just put 500 times 10 to the negative ninth meters in there. Don't change this around yet. Wait until your very end to get that significant figure, and then plug this into your calculator. Okay, so this is what we should get. Okay, if you plug it in. And unit wise, meters cancel out. So I'm left with per second, which is second minus 1, which is a hertz, which is a unit for frequency. So we can make sure we do it correctly. Okay. And so the other thing you have to keep in mind is kind of check your work. Well, if I really wanted to move this, I could move this over. So it would be 10 to the negative 7th. Okay. And then meters. And so 8 minus a negative 7 would be 15. Okay. Which is close. So I know I'm kind of on the right track. Okay. So when you're looking at C, is always a constant. It's always 3.00 times 10 to the 8th. Okay, frequency or wavelength will be given to you in the problem. All right. So the last thing, this is when we have waves. Okay, we also have particles. So what happened is, Max Planck, he was actually looking at heated objects and realized that, again, this word quantum comes up. Very, very key. It's the minimum amount of energy that can be gained or lost by an atom. And so that is super important. This is his equation. And it is to figure out how much is that quantum? How much energy can be given off, gained or lost by an atom? Okay? And so in this, E equals H, which is Planck's constant, and then F is the frequency. So it doesn't depend on wavelength at all, but you can intertwine this with that equation on the other side, or that we just did. Okay, so Planck's constant is used to relate the frequency that's either absorbed or emitted to the energy. Okay, so Planck's constant is always the same. It's 6.626 times 10 to the negative third joule second. So we can plug this in, all right? And this just will tell us what is the light that's given at any given frequency, what is the quantum that it has of energy. And it's how much light is taken in or given off. And if it's given off, it's called a photon. And that is a key vocab word that will come back again. Okay, so how much light is either being given in or taken out, which is a photon. So again, if we look back at that, how much energy will the yellow light from a few slides ahead of us before have? Okay, so E, we want to figure out E. E is energy. Okay, H is Planck's constant, which we know, 6.626 times 10 to the negative third joule seconds. And then F, we also know that from the slide before, which was 5.10 times 10 to the 14th per seconds. Okay, so again, always write down what equation are you using for the problem. Okay, rearrange it if you need to. Here, we're just going to plug it in. We have our H, which is this first number, times 5.10 times 10 to the 14th per seconds. All right, now seconds actually cancel out because this is, in the denominator. All right, So this is what we should get for an answer. All right. And if you think about it, do we do it right? Well, negative 34 plus a 14 is around 20. Okay, so we're fairly close. All right. So with these two equations, we can interchange them. We can figure out, if I don't know the frequency, but I want to figure out energy, I would have to, and I'm given wavelength, I can figure that out. Okay. This is what your homework is on. It's on the first 2 pages in your homework packet. So pages 2 and 3, not the front page, in your homework packet. So I want you to work on those and then ask me questions tomorrow. Okay. Have a great day. Mm-hmm.